Buenos días a todos, buenos días al público latinoamericano que nos sigue. Esta es la red LAFMAT, Red Latinoamericana de Física de Materia Condensada y Ciencias de Materiales, conformada por varios investigadores de distintas universidades en Latinoamérica. En Perú, la Universidad Nacional Mayor de San Marcos; en Brasil, la Universidad Federal de Pernambuco; la Universidad Federal Rural de Río de Janeiro; en Colombia, la Universidad Nacional de Colombia; en Chile, la Universidad de San Sebastián, en Puerto Montt; en Chile también, la Universidad Católica del Norte, en Antofagasta; en Argentina, la Universidad de San Martín, Buenos Aires; en Venezuela, la Universidad de Zulia; en México, el Cinvestav de México. Bien, el día de hoy tenemos la presencia del profesor Pratap Kollu, de India. El profesor Pratap Kollu estudió en la Universidad de Andhra, física, matemática, electrónica en Andhra University, en India. La maestría estudió en física electrónica, también en la Universidad de Andhra, Andhra. Y luego se fue a Corea a realizar sus estudios de PhD en Material Science and Engineering. El profesor Pratap Kollu ha tenido experiencia de investigación en el Indian Institute of Technology en Bombay, India, en la Universidad de Cambridge, en el Reino Unido, es donde lo conocí, en el Tyndall National Institute en Irlanda. También es un Newton Alumnus Fellow del Royal Society en Londres. Es un buen amigo nuestro, es un gran profesor en India, tiene bastante financiamiento, es un profesor poderoso, es a powerful professor in India, has a lot of funding in India, and is a very nice friend who is also happy to start collaboration or do research collaboration with Peruvians in all Latin America. Profesor Pratap Kollu también participó en la primera conferencia latinoamericana en superconductividad y magnetismo que se realizó en el 2016 en la Universidad de San Marcos. Este año, en octubre del 2023, del 23 al 27 de octubre, se va a realizar la segunda conferencia latinoamericana en superconductividad y magnetismo, en el cual el profesor Pratap Kollu estará dando un curso para los estudiantes. Entonces, la entrada para los estudiantes sanmarquinos de la Universidad de San Marcos es gratuita. No tienen que pagar ni un centavo. Pueden entrar gratuitamente a todas las charlas y a los cursos que se va a realizar del 23 al 27 de octubre de este año, 2023, en la Universidad Nacional Mayor de San Marcos, Facultad de Ciencias Físicas, el Instituto de Investigación de Física. Bueno, la charla que va a dar el profesor Pratap Kollu está relacionado acerca de, más allá de lo que es las baterías de litio, dónde está la actualidad, state of the art, ¿no? Entonces, lo va a dar en inglés porque no habla español el profesor Pratap Kollu. Bien, welcome Professor Pratap Kollu, and you can start share your screen and start your talk now.
Yeah, thank you very much, Luis. So it is nice meeting you, all of you here. And I think this is my second series lecture over here, and I'm happy to deliver it. So I thank my friend Luis for giving me the second opportunity to interact with you. So previously I spoke about magnetic sensors and devices. Today I'll be speaking about battery materials. So let me share my screen, and so I believe my screen is visible. So okay, so the title of the talk is Alternatives to Lithium-ion Batteries and Where Are We? So I'm obviously working here in University of Hyderabad, and I'm also Newton alumnus research fellow at Cavendish Laboratory in University of Cambridge. So then here it is like, let me give you some information about what is the genesis of this talk, or what exactly I'm trying to give it. So before that, so this is my research spectrum. I work on magnetic sensors. So I work on different types of magnetic sensors, include chain magnetoimpedance sensors, flux gate sensors, TMR sensors, Hall sensors, and also I work on 2D materials. 2D materials include graphene, mixene, hex boron, MOS2, and all these materials. So these materials I used to make composites with nanomaterials, means metal matrix materials anchored on 2D materials. So this will be like a multi-layered materials with all these nanocomposites in between. So we check it for spin glass behavior, photodegradation, means water purification applications, and also mainly we check for sodium ion applications, and also we have multiferroic applications for it. So here, if you look around, so this is University of Hyderabad is a centrally funded institute in India. So it ranks among fourth among the Indian universities. And if you look into the India map, so we are somewhere here. I believe that you are able to see this, right? So this is where we are here. And so we are here somewhere. And so we have a very big campus, and we are also called as Institute of Eminence. So I'll go towards the, so this is where we live in. So this is similar to a forest, and so we have a check dam, we have peacocks, we have deers. This is our administrative building. And so merely we are in the middle of a jungle. So, or we are living with birds, deers, water, and animals. So let me go to the introduction. So I believe you all know this French word, battery, we call it as the word battery comes from this old word called as battery. And how does battery look like, or what is its construction is? So it has two electrodes. One electrode is called as anode, the other electrode is called as cathode. And anode and cathode are separated by a distance, and in between there will be a space, or we call it as a separator. And this separator can constitute about another material called as electrolyte. So this electrolyte provides the movement of the atoms or charged ions. So the construction again is simple: a positive electrode, negative electrode, a space in between them. The space is you fill it with an electrolyte material which enhances or supports the flow of ions. So this is about this is how batteries looks like. And so the history of these batteries is it is somewhere near 1936 in Baghdad. So there is a Parthian battery. So this is called as a Parthian battery, and initial battery looks like it. So initial battery, so the rod here is the positive terminal, and the gray lines which are parallel to the rod, it is a negative terminal. And so it is filled up with a liquid. So I believe you are able to see it. So this liquid is called as electrolytes. So it dates back to 2000 years old. Means batteries are not really new, they are really old. So types of batteries. So in types of batteries, there are two different types of batteries, primary batteries and secondary batteries. So the batteries which you use in remote controls for our air conditioners, these laser pointers, all these, they are called as primary batteries. Primary batteries means you buy it from a shop, you use it after 1 or 2 months, you just throw it out once it is done. So this is called as primary battery. And the other one is called as secondary batteries. So secondary batteries means that so you could be able to use it, and after the battery is empty, again you can charge it and you can reuse it. So this process of charging, using the battery, and again charging, and again using the battery. So this is called as rechargeable batteries, or in other words, they are also called as secondary batteries. So everything has its own uses. Primary batteries are used in small applications like remote controls, your computer CPUs. So they are primary permanent batteries which will last for long time. So the other batteries which we use in homes for uninterrupted power supply. So you have a solar farm and you have to convert that energy, use it in your home. And if there is an excess energy, you have to store it. So in those cases, so you use secondary batteries. So even our car batteries are secondary batteries. They are charged, discharged, and they can be used multiple times. So you call it as cycles, number of cycles. So every battery has a certain cycle period, and up to that many cycles, so it will come really good. So one more other example of our secondary batteries are our mobile phone batteries, laptop batteries, all these are secondary batteries. So this one I have already told you, and lithium ions. So generally, when rechargeable batteries or secondary batteries or primary batteries, when they have started, what happened is that initially it is a primary batteries, and the capacity of that primary batteries is 1100 milliamps hour. So then initially one battery costed approximately $10 in 1994. So after that, in 2001, the price dropped to $3, and the capacity increased to 1900 mAh. So today, so the batteries can deliver up to 3000 mAh, and still the cost is dropping. So how does it looks like? So I have explained it in the beginning. So lithium ion uses positive electrode and negative electrode and electrolyte as conductor. So initially we discussed it. So this is the cathode, this is the anode, and there is an electrolyte in between. So these electrolyte helps in charging and discharging of the battery by transfer of ions. So this is our famous anode, which is a graphite. So graphite is a layered material, and the charges come, sit in between, and they could be discharged. So this is about, so during the discharge, the ions flow from anode to the cathode through electrolyte. So charge reverses the direction, and ions flow from cathode to anode. So this is how generally charge flows during the charging and discharging. So the battery's capacity is means how do you select a battery, or how do you choose a battery, or how do you define a battery? It is by the amount of capacity it is able to store. So if it is given by mAh per gram, and the more the electrode material contains, larger is the capacity. Means if electrode material is really high, so then what happens is that this electrode material helps in storing more number of ions, and it helps in storing this one. So there is a capacity loss over number of cycles. It is something like this. When you buy a new mobile phone, what happens is that in the new mobile phone, so when you buy it, so you charge the mobile phone fully. Then what happens is that during the early days, so one full charge, you can use the mobile phone uninterruptedly for at least 2 days. So that is, the battery is new and the capacity is really good. And what happens or what you observe after 2 years or 1 year is, initially when you fully charge the battery, you can use it for 2 days, but now, so the capacity of the battery decreases and you could store, means you could use the mobile phone only up to 1 day, something like that. So what happens is that as time goes on, when charge discharging are happening, the capacity of the battery comes down. So these are the common applications: laptops, mobile phones, electric bikes, electric cars, and all this. So we are talking about lithium-ion batteries now. So lithium-ion batteries are the foremost and the most advanced batteries that are available. So it has high specific energy, high loading capacities, long life cycle, so and low internal resistance. So it has a simple charging algorithm and low self-discharge. So these are the advantages of lithium-ion batteries. High specific energy and high load capabilities means, high specific energy means, so if you pack the battery with more number of electrode material, means more quantity of the electrode material, then it could store more energy. So high loading means you can keep on loading the electric material, electrode material, and it will not cause any problem. So low self-discharge. Low self-discharge means, so let us say that I have fully charged my battery now, and I have switched it off, and again I have switched it on my mobile phone after 2 days or 3 days, or let us say after 1 week. Then you should observe that at least 95% of the battery's specific capacity is retained. So if it shows 95% or 96%, then you say that so the battery has very less self-discharge. So, but if you charge the battery now and again switch it off and switch on after 1 week, and if you see that only 50% of the battery is remaining, then it means that the battery has high self-discharge. So this is about self-discharge. Lithium-ion batteries has very low self-discharge. So then, along with advantages, every item have disadvantages. Expensive. Expensive means that lithium is available only in certain places where like African nations like Congo, Bolivia, Bhutan, China. So mostly the lithium reserves are concentrated in specific areas. So it's very expensive. Protection is required. You might have heard about electric vehicles catching fire. So if there is no proper cooling mechanism or protection mechanism, or if they are overcharged, so they might catch fire. Aging effect. So normally, as number of cycles, means charge discharge cycles happens, the capacity falls down to 50%. So transportation problems. Generally, you might have checked it like somewhere, I think Galaxy S7 or some mobile phone. So it caught fire, and most of the airlines have banned it from carrying it. So lithium cannot be transported in bulk via airplanes. So safety concerns, that is the same thing. Sensitivity to high temperature. So when you park your electric vehicle, let us say that in India summer, where temperature can range up to 45 degrees, so the vehicle will catch fire. So higher the temperature, the risk of catching fire or exploding is always higher. So what we try to do in our lithium-ion batteries is, so we try to check secondary lithium-ion batteries that have been investigated, and to achieve higher energy density and power, metal oxides are used as anode materials, and metal oxide conversion anodes should enhance storage capacity. So we have chosen metal oxides, but which type of metal oxides are good? So we have chosen spinel cobalt ferrite as an anode material, and it has a severe drawback from capacity fading. So to overcome these problems, we have made a composite of carbonaceous materials and cobalt ferrite. So we have fabricated in different morphologies and all this. So this is our experimental outline. So we have fabricated porous cobalt ferrite. So it is embedded with different concentrations of graphene. Means initially we started with pure cobalt ferrite. We have added 10% of graphene into it. That is second sample. We have added 20% of graphene into it. That is third sample. We have added 13% of graphene into it. That is fourth sample. We have added 40% of graphene into it. That is the fifth sample. So we have prepared cobalt ferrites with different graphene compositions. We have did electrochemical characterizations, and what we found out is cobalt ferrite with 20% of reduced graphene oxide with sodium alginate binders has exhibited very good electrochemical properties, high reversible capacities, and excellent cycle performance. So the theoretical value or theoretical capacity value of cobalt ferrite is 914 milliamp hour per gram. And we have used sodium alginate as binder. So this is mentioned here. So this is the synthesis procedure, graphite. So this is the advanced Hammer's synthesis procedure. And graphite is changing into graphene oxide. So we have added metal precursors, and after adding the metal precursors and following the hydrothermal route, so this is the graphene oxide. The blue one is the graphene oxide, and the violet one are the nanocomposites, cobalt ferrite nanocomposites on it. So cobalt ferrite nanocomposites are anchored onto the reduced graphene oxide flakes. So this is the structural and morphological studies. So bare cobalt ferrite, 10% RGO cobalt ferrite, 20% RGO cobalt ferrite, 30% RGO cobalt ferrite, and 40% RGO cobalt ferrite. So everything showed really pure peaks of cobalt ferrite formation. And this is the FTIR. So again, the same thing. Black one is the pure cobalt ferrite, red one is 10% RGO plus cobalt ferrite, green one is 20% RGO plus cobalt ferrite. The dark blue one is 30% RGO plus cobalt ferrite, 40% RGO plus cobalt ferrite is somewhere here in maroon color. So we have obtained the 1580 characteristic peak. This is the characteristic peak which can attribute to the carbon backbone. So whenever we have a 1850 peak, then we can say that so there is a carbon composition in it. Then what happens is that you could look it clearly. So this 1850 peak intensity is increasing, and this shows that the amount of RGO that is present in it is also increasing. So the other bands 3380 and 1349, this is 3380 and this is 1349. So these are attributed toward the OH stretchings. And there is one more band at 1209 and 1083. So these are C and OH stretching vibrations. And there is, you observe a peak here at 584. So this 584 is assigned to the MO band in cobalt ferrite. So this is about the FTIR. This clearly confirms that we have prepared cobalt ferrite with different RGO compositions, and RGO compositions are increasing. So this is our Raman, and generally, if you have a RGO, so it is confirmed by D and G peaks in the Raman band. So here are the D and G peaks. So D peak is having the highest intensity, and G peak defects peaks and these peaks. So the formation of RGO is confirmed here, and this is clearly showing that porous cobalt ferrite with RGO is successfully prepared. Now, after that, we took the SEM, scanning electron microscopy things. So this one, if you look into the C figure, so this is the RGO flakes, and nanocomposites are attached to it. RGO flakes and nanocomposites are attached to it. So you could see clearly the FESEM images for all these different compositions of RGO. And so this is the EDS spectrum. So it is clearly showing that cobalt, Fe, and oxygen, they are present in it. So this is the HRTEM, and in the HRTEM, so you could clearly see that. So these are the flakes, and these are the particles, cobalt ferrite particles. So these are the electrochemical properties. So electrochemical properties means these are the done by the potential static equipment. So coin cell is fabricated. We fabricate a prototype device, and this prototype device is tested by using a potential stat. Means we apply the voltage from 0 to 3 volts, and you see how much current is passing through it. So this graph is for pure cobalt ferrite. This is for 10% RGO, 20% RGO, 30, 40, and 20% RGO with alginate binder. So 20% RGO plus alginate binder, it is showing a clear area where so it can store the energies. So this is about charge discharge plots. So here you say that you are giving 0.1 C of current, and you observe the capacity as 800, means you fabricate a coil cell and you are giving 0.1 amps of current to it. So when you are giving 0.1 amps, so what happens is that the capacity is around 800. So you are increasing the current, capacity is decreasing. You are still increasing the current, capacity is decreasing. Still increasing the current, capacity is decreasing. So you kept on increasing the current, and you have observed that so the capacity is decreasing. Then if now what we are trying to do was, again, we are trying to give the same current which we have applied initially. Then this is to check that, look, we have increased the capacity of the current, and is the battery damaged because of increasing the current? So then here when we apply again 0.1 C, what happens is that we have gained the same capacity, 914 mAh per gram. And this shows that merely by increasing the current, so your material is not damaged. So generally, I think everybody knows it, you who are using the electric vehicles. So they say that slow charging. So you should leave the vehicle overnight and it gets charged. Or there is also option for fast charging. So you can choose the fast charging option. Then they will warn you that, so whenever you do fast charging, after one fast charging, you have to do at least 5 or 6 slow charging. Otherwise, what happens is that the anode materials and cathode materials within the battery, they get pulverized and capacity will drastically decrease. So here, our material exhibited very good stability towards changing current. Even though we have changed the current, the material did not get damaged and retained its own capacity. So what we achieved, so cobalt ferrite with RGO samples, we have successfully synthesized, characterized, and cobalt ferrite with 20% reduced graphene oxide with alginate binders delivered 1040 mAh per gram, milliamps per hour, milliamps hour per gram at 0.1 C. C means current rate. So, which is almost near to the theoretical capacity or more than the theoretical capacity. So this is more than the theoretical capacity because there are alginate binders in it. So then it is something like, so lithium is very scarce and its costs are increasing and the raw materials associated with it are also expensive. So everybody is looking for alternatives to lithium ion. So if the world should get zero carbon emissions by 2050, so we need almost 2 billion electric vehicles and the existing lithium supply cannot do it. So what we are also trying to do is we are trying to look for, is there any alternative to lithium ion? So alternative, so this is the worldwide lithium demand. So look at 2023, the demand is 685 metric tons. And by 2030, it would be approximately 2,200 metric tons. So this is the demand for lithium and there are no enough reserves for it. So rechargeable batteries market will reach approximately 150 billion globally. So this is given by Bloomberg. And so, and when you are looking into lithium ion batteries, so lithium ion batteries doesn't come only with lithium. There are many other materials, copper, aluminum, graphite, nickel, cobalt, lithium, and manganese. So these materials are also very expensive. So yeah, this is what I'm saying, access to raw materials. Lithium, 75% of lithium is in Argentina, Chile, Bolivia, China. Cobalt, 65% of the cobalt is from Congo. Carbon, 65% of flakes of graphites are mined in China only. Nickel, so Indonesia is the biggest supplier of nickel. And in 2014, Indonesia has banned supplying nickel. So prices have increased drastically. So then what are the other materials which we can look, which are naturally abundant, less cost and all this. So then, so I believe you are able to see this: sodium, magnesium, aluminum, silicon, potassium, calcium. So these are the materials which are abundantly available in nature, which can be tried for other battery chemistries. So this is the battery chemistry, and in 2019, Nobel Prize is for lithium-ion batteries. So what are the other things? So other things were sodium. So sodium can be used. So here, sodium-ion batteries are almost fabricated. Pilot plants are there. And we are also working on sodium-ion batteries. So sodium-ion batteries will not be having much capacity as lithium-ion, but they are very safe. They are less expensive and all this. So this is the natural source for getting the hard carbons. Hard carbons are used for electrode materials. So instead of getting materials from chemicals, you can directly source them from natural materials like hard carbon anodes, cellulose fibers. We need electrolyte separators, so we can use cellulose nanofibers. So all these separators can be sourced from natural things. So this is about sodium-ion market. Sodium-ion market is expected to grow at least by 20% from 2021 to 2030. So rechargeable batteries needs priming. It's not really true. And unplug it from the charger once it is fully charged. Leaving charger connected will blow up the battery. So generally, it's not true. Manufacturers will build some circuits in it such that it could cut off automatically. So before recharging it, so you should drain everything, memory effect. So memory effect is only in particular batteries. Something like if you fully drain the battery, there is a myth that it cannot be recharged. But that's not completely true. It is in nickel cadmium only. So the other alternatives are aluminum ion batteries. So where aluminum is used as anode and graphite is used as cathode. So AlCl3 is the ionic liquid that can be used. So in our lab, we are working on sodium ion and aluminum ion batteries. So these are the alternatives to aluminum ion batteries. And also magnesium ion batteries are promising. So they are affordable, abundant. So in magnesium ion batteries, Mg is the anode and the graphite materials are the cathodes and they are electrodes. So Mg is having the very good capacity of 3833 milliamps per hour per gram. And if we are able to develop good batteries, Mg ion batteries will be really good. So I think I'll end it up here. So if you have any questions, please ask me. Thank you.
Thank you, Professor Pratap Kollu. Very interesting talk. Now it is time for the question from the panelists. Before, voy a invitar a los estudiantes y al público que nos está siguiendo a través de las redes sociales de distintas universidades, que pueden ir dejando sus preguntas a través de las redes sociales donde han venido siguiendo esta transmisión. Al final de las preguntas de los panelistas, vamos a pasar a leer las preguntas del público. Perfecto. We are going to start now with the questions from the panelists. Okay, first, we have Professor Andrés Ramírez from la Universidad de la Frontera, from Chile, from Temuco. Andrés Ramírez, you have questions? Your camera, Andrés Ramírez. Not here. Andrés Ramírez. Well, Andrés Ramírez apparently is not here. We continue then with the same university, Professor Jonathan Cisterna Garcia. Jonathan. Jonathan Cisterna, your microphone, please.
Yes, I am here. Sorry.
Yeah,
I
your camera, please, Jonathan.
Activate my camera. Yes. No problem. It is okay now?
Yeah, go ahead with your question.
Okay. Sorry, my apologies. Just a little correction. I am from the Universidad Católica del Norte. So, okay, Mr. Cole?
Yeah,
Is
it's
that-
okay. No
It's
issues.
okay? Okay, Mr. Cole, thank you very much for your presentation. It's very interesting. I have two questions about your presentation concerning the perspective of the magnesium and aluminum batteries. About, for example, what is the insight about the solid state batteries? Because it's supposed that you can the future in the energy storage device is the solid state batteries. So the
Yes.
question, what is the perspective in this type of batteries to the possibility to make, for example, solid state batteries?
Solid state batteries can be made, but these batteries are for mass requirements. We call it as mass requirements. Let us say that there is a place where there is a solar farm. So solar farm of 10 kilometers by 10 kilometers area, you have a solar farm, and what you will do was, so you have to store the energy and you have to transfer that energy to some other places. So maybe within 50 kilometers, there is a small village which needs some power at the night time. So what you do was, generally lithium-ion batteries are very expensive. You cannot, what do we say, afford that many batteries. Let us say they might need around 10,000 or 25,000 batteries. And even carrying lithium-ion batteries is not safe. So here, what you can do is you can carry the sodium-ion or magnesium-ion batteries without any problem, or aluminum-ion is the safest of everything. But lithium-ion blasts out. So this is where we are trying to check in, so mainly in electric vehicles. But solid-state batteries, you are right, they are the future, but still considerable progress is not made.
Okay, thank you. My second question is about, for example, in the same topics. It's concerning to the solid state electrolyte, because, for example, I don't know if you know that for magnesium batteries, I have some issues in the liquid electrolyte, specifically for stabilize the magnesium ion in organic solution, because not all the magnesium salts are soluble in some organic solvents. So there is some works in your research group, for example, about solid state electrolyte for magnesium batteries.
For magnesium ion, solid state electrolytes are very difficult. Why? Because the transfer of ions is very much limited in solid state things. So as of now, I don't think that there is something in it. So for magnesium ion, so still I believe that lithium ion is being used or tested for solid state, but for magnesium ion, I'm not exactly sure. There are few electrolytes which are commercially available and which we are always trying to buy it out, and maybe I can share those things with you. I think I have some materials with me. So if you want magnesium ion electrolytes, so they are, I think, just hold on. I think I have something with me, magnesium electrolyte, LICL, I guess, LICL. And there is one more thing, MgCl2 is also there. What else is there? I think MGTFS ISI should also be there. So I'm exactly not sure, but I'll share you these materials. So these are like 1 molar of LiCl and 0.4 molar of MgPHCl3. I'm unable to recollect. These are the electrolytes which we have used for magnesium ions. But solid state, I am not sure.
Okay, no problem. Thank you very much, and congratulations again for your
Let's
presentation.
be in touch because we are also working on the same thing.
Okay, thank you, Luis.
Bien, muchas gracias, Jonathan Cisterna, de la Universidad Católica del Norte, Antofagasta, en Chile. Now, the same university, we have Professor Alifer Mestra Acosta, I think he from Colombia, but is in Chile. Alifer, are you there? Your camera, please. Alifer Mestra.
No question.
No question. Okay, Alifer, no problem. Okay, now let's continue with, let's go to Mexico with the Simba staff of Mexico, Professor Arturo Martinez. Arturo. Your camera, Arturo. Okay, go ahead.
Good morning, Professor Frank. Many thanks for your presentation. You presented very nice data for the lithium-ion batteries and the market. I have only one question about have you studied any material for the lithium-ion cathodes that avoid the use of cobalt?
We have tried all the spinel ferrites. So nickel ferrite with RGO, zinc ferrite with RGO, cobalt ferrite with RGO, zinc ferrite with RGO, everything we have tried.
Okay, and what about results? Better or?
No, means nickel ferrite is not really good. Zinc ferrite is wonderful, means same as compared with cobalt ferrite. And magnesium ferrite is also good. And magnesium ferrite, we have tried it for sodium ion also. So they're mostly okay, means all the spinel ferrites, they're almost of the same kind, so they're okay. We have tried most of the materials in lithium ion. So actually currently means due to funding issues, we are not getting any research funding in lithium ion. So since almost 5 or 6 years, I have moved to the sodium ion and magnesium ion.
Okay. Many thanks, Professor, for that.
Okay.
Congratulations.
Thank you.
Thank you, Arturo Martinez from Simba staff from Mexico. Pratap, let me tell you that Professor Arturo Martinez, he is also going to participate in a conference in October. You will meet him there.
Okay, great. Mexico. Nice to see. No.
Professor Martinez. Well, okay. Now let's continue with. Let's see if there are questions from Colombia, Universidad Nacional de Colombia. Ximena Velázquez. You have questions, Ximena?
No, in this moment we don't have questions for Professor. Only thank you for all this conference.
Excellent. Okay, let's continue. Let's move to check if there are questions from the public. Melvin, are there questions from the public?
Profesor Luis, bueno, gracias. Profesor, saludos, profesor Pratap. No tenemos preguntas como tal, solo felicitaciones por la presentación. Gracias.
Okay, thank you. Well, Pratap, I think that maybe it's out of the scope of your talk, but I have one doubt. Do you know
Yeah.
something? Do you know something about how to take the lithium from the lithium ores? Lithium ores are composed mainly by lithium carbonate. Do you know
Yeah.
something of how to get that lithium from there? Any kind of process, maybe chemical process?
No, means there are a few organizations here, and some of them are already working on it. So maybe if you need some information, I can give you.
Yeah. Well, because end of next month, we are planning with some group of researchers to go to collect also lithium ores from Peru. Peru also has some lithium, similar to Bolivia. We have lithium as well,
great.
to collect that and then to try to analyze and later to use in batteries or so on, because in the batteries, lithium or other alternatives are very interesting for cars, electrical devices, no gasoline cars, and that is the
Yeah.
future. Yeah.
Great.
Okay. Well, Pratap,
Let
thank you
me know
very
if
much.
you need anything, I can share it.
Excellent, because you are going to be there in Peru next month. Well, let me tell you about the next talks, please. That we have for next Saturday and so on, and you are also invited to participate on it. Okay, I will tell to the public. Para todo el público que nos sigue, el 23 de septiembre la charla será de la doctora Alejandra Navarrete de la Universidad Metropolitana de México. Su charla está titulada Diseño de nuevos materiales usando la teoría de funcionales de la densidad. El moderador será el profesor Felipe Mundaca de la Universidad de San Sebastián en Chile. Ese es el sábado 23. El sábado 30 de septiembre, la charla estará a cargo de la doctora Lídice Bayant, de la Universidad de La Habana, en Cuba. El título de su charla es Óxidos semiconductores nanoestructurados mediante técnicas de bajo costo para celdas solares emergentes. It's another talk about solar cells, Pratap. You are invited the 30th of September. One professor from the University of Havana, Cuba, is going to give on Saturday 30. Okay. El sábado 7 de octubre, la charla estará a cargo del doctor Lauro Bucio de la Universidad Nacional Autónoma de México, la UNAM de México. El título de su charla es Animaciones, videos y modelos 3D para el estudio de las propiedades de simetría dada por el Grupo Espacial de Especímenes de Cristales, con el profesor Lauro Bucio de la UNAM de México. El sábado 14 de octubre, está por confirmar aún, tendríamos la presentación del doctor Igor Fier del Quantum Design para Latinoamérica, que estaría presentando algunos nuevos productos del Quantum Design en línea. Está por confirmar aún esa palestra. El día sábado 21 de octubre y el sábado 28 no habrá charlas en línea, debido a la organización de la segunda conferencia latinoamericana en superconductividad y magnetismo. On October, Saturday 21st and Saturday 28th, 2023, there will not be talks, online talks, because of the organization of the second Latin American Conference on Superconductivity and Magnetism, which is held at the Faculty of Physics of the University of San Marcos in Peru, in Lima, Peru. Well, okay. Pratap Kollu, do you have any maybe further speech to say goodbye maybe to the people? Your microphone, Pratap.
Yeah, okay. So thank you very much for inviting me. It is nice to be here for the second time. So if anybody is interested in collaborating, you are most welcome. So I work on batteries, means these 2D materials, nanocomposites, I also work on multiferroids, thin films, sensors, water purification. Maybe if anyone is coming to the conference, hope I'll meet you there. But if you want to talk to me regarding any collaboration, please send me an email. I'll be happy to see if I am able to collaborate with you.
Okay, thank you very much. People who are more interested in the work of Pratap Kollu, he's going to participate in person in Lima en 23 y 27 de octubre en Perú. Las personas que están más interesadas en el trabajo del profesor Pratap Kollu, él va a estar en 23 a 27 de octubre en Lima, Perú, en la Universidad de San Marcos, participando en la conferencia. Muy bien, muchas gracias a todos, nos despedimos. Ahí está Alifer Salim Mestres, está bien, por favor, abran sus cámaras para decir chao al profesor Pratap Kollu. Les digamos chao. Ok, bien, cortamos la transmisión.